Hello. Thanks for coming. So we have at least three people, right?
I have 4.
Okay. So Zhao Fan, Yang Chao,
Yeah.
and
Amy.
oh, I see. Raju is from online, and I hear the. It seems I'm hearing the voice of Amir, but I do not see him. Okay. So let me check if you have projection of slides on the screen. Oh, I know I need to push a button to share screen. So do you see the screen, my slides right now?
Yes.
You do? I hear the voice of Amir, but I do not recognize the words.
He is finding the link.
He needs a link once again?
Oh, 1 second.
I can resend it.
Oh, yeah.
Okay. So we are continuing to go over the materials, over the concepts and materials for the Hartree-Fock theory, and you have been exposed to it to some extent during yesterday lab. By the way, how did it go?
Not bad. Pretty good.
Okay, thank you. I'll tell to Dr. Han that he did good job. So you see that launching calculations is not complicated, and for small system it goes quick, but we need to still pick up several ideas to get an understanding how it works. And major concept for today will be so-called variational theorem. Please give me a sign if you ever heard about it. Variational theorem. That's okay. Sometimes it is used in heavy construction engineering when one calculates the like shape of like beams so that they do not break. It's quite general mathematical concept. And if there will be time, the goal, and we'll talk informally before I go to the slides. The local tasks of our stream of information is to combine the mean field concept and antisymmetry principle. We agreed on this, and I'm not declining this plan. But there are several little things that we need to go over to complete this combination. And by the end of today's meeting, so let me explain by lay language what we are going to get. The multi-electronic wave function is chopped as a product of single electron orbitals, right? We already established a Schrödinger equation that includes mean field of all but one electrons on the last electron. So we can generate one electron orbitals that inherit signatures of the electrostatic interaction with the rest of electrons. And we do know that one can combine the one electronic orbitals by setting up a product to form multi-electronic wave function. Probably one needs to do it in the respect to anti-symmetry principle as a Slater determinant. But here is a little challenge, a little open question. The equations that the principles that we are describing will work with guarantee if we have already found correct wave function and correct orbitals. But if we didn't start from right point, how do we get these orbitals? Because look here, in order to get equations for one electronic orbitals, we need to know the state of all other electrons that will create field. But if you just approach problem, or if the computer just starting it, where to take the orbitals for the other electrons? One needs to start somewhere. And when so one needs procedure, how to, so we will get an input if we will get an output if you get a right input, but where to get the initial field? We need to do something approximately. So the idea behind the numerical procedure for Hartree-Fock theory that the orbitals and fields that of all but one electrons need to be systematically improved from bad approximation towards ideal result. And in this way of iterative improvements, one needs some lighthouse, some compass, some general directions. What does it mean to improve and how to improve orbitals? Like how technically one can improve orbitals. And the practical procedure of improving something that will match some criteria is coming from variational theorem. In lay language, it means you vary things that are not ideal until they become ideal. And for each variation, you have a criterion. Does it make sense? Or it is unclear? Okay, so vary something until it becomes ideal. Okay, and now let me go to slides, and please give me voice signals if you want me to stop, because I will try to stop and look on your faces, but I can get excited and forget about it and start mumbling something too quick. Okay. So we want to describe properties of materials, and we are in the, let me shift it a little. No, maybe my hands on variational principle. Yes, lecture number 12. We are on the variational principle, and when I get back, we will fill this form who presents what. So just keep it in mind. There is a little homework to entertain you on weekend, but according to what I've heard from Dr. Han, and I was watching, I was connecting to your lab for a couple of minutes. I saw you almost, you basically completed it, right? So let me, so I've seen that you already completed, so I've added a couple of things so that you do not feel bored. But basically, you create several models, and as a entertainment, you can also add to this list the models that you already have from like homework 1 or 2, this chemical reaction. And then for each of these models, run single point Hartree-Fock, and then analyze output. Like for each model, find energy and total energy and energy of HOMO, LUMO, and band gap. So let me quickly give a heads up on importance of HOMO and LUMO. Did Dr. Han tell you about so-called Koopman's theorem? No?
I don't think so.
Okay. Did he told you what is the meaning of finding HOMO and LUMO according to what you've heard from him?
The occupied and the virtual.
Yes, occupied and virtual, and their energy offset determines the color of the material. Like 1.8 electron volts will be red, corresponding to red color, 3 electron volts correspond to blue color, and more than 3 electron volts correspond to like white transparent. And less than 1.8 will be like the black intransparent. So it's one of the physical properties. So just by doing this simple calculation, you can already characterize, make some basic characterization of the material. Let me check if you have heard about such experiments as electrochemistry. Mahik tells that she heard about it, right? Electrochemistry. No? It is when molecules are put in electrolytic bath, and voltage is scanned and current grows non-linearly or drops non-linearly. So there are experiments that respond to a procedure of adding or removing electron to a molecule. It's ionization energy, like how easy is or how hard is to take an electron from the sample. You may have heard about this parameter in photoionization. Like if you hit a sample with a quantum of light, how energetic, what's the color of light should be in order to throw electron out of the material, to ionize it. And there, so I suggest that you look online for Koopman's theorem and maybe copy paste one sentence what it is as you find. But I will tell right now that these energies of HOMO and LUMO are related to real life, to a practical observables of electron ionization energy. So for conductivity materials, for solar cells, it is important observable. And I think you have already plotted band gap as function of size of the model, right? Or you watched Dr. Han doing it. So please try to process your data and look how the band gap looks on as function of the size. So it is expected that the larger the model, the smaller the gap. But maybe by some reason you find deviation from this. What else? And when we meet next time, did Dr. Han explain you how to do density of states, or you stopped? You didn't cover it.
I don't think so.
Okay, then I'll cover it. So do not bother to do it. If you really want, you can, but it's fine to skip until later. Okay. So what you did in the lab was analyzing Gaussian output, and this ionization energy and electron affinity are basically HOMO and LUMO energies. So you build a model, run a specific basis set specific method, and found that there are alpha and beta, and you were identifying the numbers where once you see the numbers increase, and when it goes from occupied to unoccupied, it's most interesting fragment of the model. And if you subtract them and convert into the electron volt units, it is something that you can already publish, earn you a piece of bread, get hired. So, and you can stop the course and start earning money by your scientific activity, by electronic characterization of materials. Okay, and we are adding one more concept into our mainstream. So before we implement antisymmetry into our electronic structure process, we need to throw in so-called variational theorem. So we are solving this multi-electron Schrödinger equation. We seek for solution in form of Slater determinant, and we practice mean field concept, so that next electron will take a different orbital compared to previous one because of the repulsion. And this, so it is, we also practice the concept of expectation value. We did a monster operator, which is partially number, partial operator in respect only to one variable. And with this monster operator, we did formulated this equation that acts only on one orbital, while all others, like orbital 2, 3, 5, if they are present, are included into this auxiliary one electron Hamiltonian. It's not the full Hamiltonian, it's one electron Hamiltonian. So the challenge that you were not objecting is that in order to find phi 1 in here, in this equation, one needs to know phi 2 in finding this average field. And generally they are unknown. One needs to start somewhere. So we will need to formulate this so-called self-consistent cycle, but these Schrödinger equations tell us how to find one electron function, but we need to set up a loop algorithm similar to optimization, but for optimization of these orbitals rather than positions of ions. So we are starting the lecture right now, and this is the one half-page screenshot from a book that I was bringing in the class. So, sorry. But it is so brief that it is hard to perceive. But this equation 29, like E of one symbol is bigger than equation of other symbol, is basically what we are going to cover today. So how to find total energy of the multi-electron system if we already know multi-electron wave function? We do need to practice expectation value of Hamiltonian. And since there is no guarantee that our wave function is normalized, we may divide this expectation value procedure onto this normalization. So then it will be a reasonable observable upon practicing this trick. So how to interpret this equation? So the idea is very quick. So I'm speaking for like 40 minutes about a thing worth of 1 minute. if we do know wave function and if we do know Hamiltonian, then we do know the energy, right? Let me check if everyone is okay. So as soon as wave function is known and Hamiltonian is already set up in stone, multi-electron Hamiltonian for all electrons, we do have a procedure to find expectation value of Hamiltonian, which is total energy. So if we arbitrarily design shape of wave function, we will still can get out of it some energy. If you find ideal solution, we will also have some energy. And here is the theorem. Here is the theorem. If we increase, if we add a little addition to our ideal to our ideal wave function, like we have ideal wave function which is already solution, and we do add a little arbitrary small increment, then the total energy must increase. Like here is an illustration. Suppose that psi naught is will be a maximum in it's all for multidimensional things, but in some region of multidimensional thing wave function it will be like a maximum. Then we add a little addition in other things, and then new wave function will have more complicated structure. So that the theorem is that if you find expectation value of Hamiltonian, the total energy, in the ideal wave function, that is absolutely correct solution, and in any wave function that is different from ideal wave function, the total energy in this different wave function will be bigger. Basically, it is the same idea as we already practiced in the optimization. Like if we know that total energy in the minimum of potential is the lowest, any motion away from this potential will increase the energy. Does it make sense? So if you know for sure that correct wave function exists and there is a ground state energy, then any change of the wave function will lead to increase of the total energy. Okay? So this concept, I understand it is very childish, very simple, but it is important and helpful. So this theorem, it's called variational theorem, gives us a compass, to improve our wave function. In some sense, we can forget anything we did up to now. Write a little code which will fabricate multi-electron wave function with the random numbers at different grid points. And then we generate wave function as like random numbers, plug it into the procedure to find total Hamiltonian, and record what will be the total energy. And then we use another set of random numbers, another set of random numbers, and then we find set of energies and we select the random wave function which gives the smallest total energy, and it will be correct answer. The only problem that for multidimensional space we need to toss random numbers for too long time. But this minimum of energy, by some reason I see that images are frozen. Please tell me if you do not hear me. Please tell me if you hear me. Uh-oh. I probably need to reconnect. I will stop and come back once again. Okay, I see. I hear the background noise. It was probably interruption in the transmission, right? Okay, so I'm coming back with the slides. So if we have increase in energy, increase in wave function, and it doesn't matter whether it's complex, positive or negative, it will be bigger total energy. And we can find wave function just by random numbers. So in some sense, we already got main thing from today's meeting. But I'm going to introduce a little concept which is less fundamental but very helpful. So, and again, we probably need just to talk it face to face. We already talked that atomic wave functions, like hydrogen atom wave functions, are building blocks to build everything. On one hand. On another hand, in a molecule or in a material, electrons take delocalized space. Even one electron can delocalize over many atoms. Therefore, one needs to add together many atomic wave functions to form so-called molecular orbitals. So linear combinations of atomic wave functions form molecular orbitals. And this is one of the ideas that we need to add to our repository. So the atomic wave functions can be called chi, I used the letter chi here, sub A, and they're centered where the atom is centered. The coefficients A, in some sense, it's all atomic quantum numbers: principal, orbital, magnetic, and spin. I just put them in the letter A because otherwise it will be too many numbers. So if we add together, so this is summation, if we add together several basis functions, several atomic functions with certain coefficient, and each coefficient should be capital I. No, not capital, lowercase. It should be upper I here, yes. So we add together these atomic wave functions with certain weight coefficients. And this will be a superpositional molecular orbital for electron delocalized over several, composed of several atomic wave functions and delocalized over several atoms. So when we search for multi-electron wave functions, we cannot change procedure by Slater. We use one electron wave functions in a certain procedure. We cannot change Hamiltonian, and we cannot move ions. We cannot change hydrogenic like basis functions. So, but we need to improve our solution. So the only thing that is allowed for us to improve, to change, are those expansion coefficients. So this C sub ij and super index A are parameters that we can optimize. And J is index of molecular orbital, which was like 24 and 25 for your first example of molecule of titanium hydroxide. Like I can run from 1 to HOMO and then from LUMO up further. So please let me know if this little notation and if this concept seems reasonable or you want more comments. So, oh, you don't care. So very soon we will set up a procedure that will optimize these C coefficients, and it will be very similar to optimization procedure for geometry, but instead of atomic coordinates, we will optimize these expansion coefficients in front of atomic wave functions. And the procedure of the Hartree-Fock theory will be, so here is the, how to say, assembly line. When we write the calculation, we start with positions, with atomic coordinate of all atoms in the system. Then we already know from tables atomic wave functions around each atom. Then one needs to get somewhere this expansion coefficients. And with the expansion coefficients, one can form molecular orbitals. And then one can practice Slater determinant procedure to set up multi-electronic wave function and find total energy. So in this streamline, the only thing that we are allowed to change is the C coefficients, and subsequent because all other procedures and elements are already set in stone. So in some sense, Hartree-Fock theory is the theory to find atomic wave function expansion coefficients, how atomic orbitals are converted into molecular orbitals. Okay, this is still the same idea. So we can change atomic orbitals. We can change expansion coefficients, and then the rest goes through prescriptions. So Hartree-Fock theory is application of variational method of variational theorem to find expansion coefficients until one arrives to the minimal total energy. And do not worry if you do not see the whole picture. We are trying slowly but surely through several distances. It's like making a siege of enemy city and encircling it with our forces. So the procedure, the Hartree-Fock equations that computer is solving for us is iterative procedure, same as optimization. It is called self-consistent because the field created by all occupied orbitals, all electrons sitting on the occupied orbitals, and shape of the orbitals should agree to each other, should be consistent with each other. And this self-consistency is achieved by finding expansion coefficients. Okay, what else? Another little concept. When we were starting today's meeting, we started with an equation for one electron wave function. I'm going to run over all slides and go to the first where we started. So everything that is encaged in this brackets is an operator that acts on one electron wave function. So it's only one electron. It's negative charge. But this operator is related to Hamiltonian for all the electrons. Not to a full extent, but it keeps traces of the occupied orbitals. So it is not Hamiltonian, but it is like Hamiltonian. And in the community, there is a convention to call it F. Like total energy is Hamiltonian operator, and this one electron energy for one in Hartree-Fock theory is Fock operator. Fock operator or Fock matrix. Okay, I'm going back to where we stopped. So we are going to solve this Fock equation with Fock operator to find one electronic orbitals. Then out of these orbitals, we are going to find electric field, electric potential, and then plug it into Fock operator once again, and solve it again. And the procedure to stop this operation will be achieving the minimum of energy. So one repeats this orbital, Fock operator, orbital in a cycle wise, same as the programmer in a bathtub. And criteria of success is that total energy stops changing as we go through. So almost the end. Okay. Let me check how happy you are with this concept. I see from your smiles that you are very happy, and I have a little bit more of new information, but I do not want to go too quick so that no one is discouraged. So, and I will repeat it coming in person on coming Tuesday. So probably you will not. You will get more and more happy about this concept. So, the simplest theory for electronic structure is Hartree-Fock theory. One needs to find multi-electron wave function. And multi-electron function is composed for one electron orbitals, but these one electron orbitals are not on single atom, but they are constructed as molecular orbital with a superposition of several atomic orbitals. And the percentage of each atomic orbital contributing to molecular orbital is our parameters that we need to optimize. Criterion to stop or continue this optimization of parameters is total energy. It needs to be minimal. And the mechanics of finding these orbitals again and again, and for finding total energy again and again, is so-called Fock equation, which is projection of multi-electron equation onto one electron equations. So this Fock equation includes traces of electron repulsion with all background electrons acting on our last electron. Good? Okay. So this thing that I will superficially go through quickly now and we'll focus in details when we meet in person is how to combine all this multitude of ideas with antisymmetry principle, because antisymmetry principle is not avoidable. So, SD is not South Dakota, it is Slater determinant. VEE is interaction between two electrons. So, and you recognize Slater determinant, first orbital, first electron, second orbital, second electron, and then antisymmetrization. Second electron and first electron and second. When we need to find total energy, we practice Slater determinant from the left, then operator, then Slater orbital on the right. If we take only green, open the brackets and take only the first term, then no, let's go further. Yes, only the first term. When index of electron and orbital coincide, the sign of this term will be plus, because electron number 1 on orbital 1 and electron number 2 on orbital 2 do repel each other. Let me see that no one is objecting. 2 electrons repel each other. So the sign of this term will be positive. But now let's take, I'm going backwards one slide. Now I'm going to take a term that will include first here and last there. So this term will include minus sign, but it still be a contribution to Coulomb interaction energy. So if I go to the term number 2, we have on the left first electron in first place, and on the right we have first electron is already on the second place, and the second electron is in here, and here it is moves to another orbital, and upon this swapping in the term we are yielding the negative sign. So this contribution, this term contributing to the Coulomb interaction of 2 electrons will have negative sign. You see it, right? So because of antisymmetrization, there will be additional term in the Coulomb electron Coulomb interaction that has negative sign. And in order to, it's throwing off. 2 particles of the same sign should repel, should have positive energy. But there is a part of the energy which corresponds to attraction of electrons. It's very crazy. And in order to simplify, to prevent humans from becoming crazy, there is a terminology. When it is good old-fashioned Coulomb, a term in the Coulomb interaction that repels electron, people call it true Coulomb, just Coulomb, without any. And the part of the interaction when there is a minus sign, it is called exchange, because electrons swap the orbitals. So if we consider quantum properties of many electrons, the total energy accumulates a so-called exchange term, which has a stabilization nature. It brings total energy down. And from molecular dynamics, you know that lower energy means more stable configuration. If there is a mechanism that makes energy lower, it means that your system will be more stable. So in addition to Coulomb mechanism that pulls electron away, there is an exchange term that brings them together. And this is one of the key factors of the Hartree-Fock theory. If we remove this exchange term, it will be just Hartree theory, which is beautiful but wrong. And if you add this antisymmetry exchange, then it will become really powerful. And for today, it is not the best, but it is not the best in precision, but it is best in qualitative trends, and is the best in the logical consistency. So it has all main components that electronic structure theory needs today. Let me see if I have more slides, but I think we are arriving to. So here, electrons are swapped. On the place where it was 1, now we have 2. On the place where it was 2, there is 1. So it is exchange between spots. So electron jumps from one orbital to another one, and it is not actual jump. It is just consequence of Slater determinant shape of the multi-electron wave function that we have accepted by democratic votes. Okay, I think it is enough for today. So I'm done with all materials. We'll may send you some maybe emails with recordings if it was successful. And here I can stay a few minutes more to answer questions.
Thank you. Excuse me.
Yes.
General question. Each part of the lecture, each session you cover usually from a different book. So
please repeat. Each part of the lecture?
Each session, for instance.
Each session, okay.
Yes. So is there any book, if we want to have a review from the start of our course until now, to have a brief review on them, is there any book that cover all materials that you present?
No. I collect materials from different books. Maybe in a couple of years I will write my own book that will collect, but right now it is not available. I'm trying to take cream of the cream from different books.
Okay, good.
But thanks for asking and suggesting me to write a book. You can become you can become a co-author.
Sure.
I'll provide all materials and you just add a little transitions and more text.
Okay, sure.
And then we will become rich by selling this book to all universities and students.
Really? Okay, why not?
More questions on the either course material or labs or any general questions? Questions 1, question 2, questions 3. Okay, then have a pleasant weekend. And
thank you. You too.
Thank you. I look forward to seeing you on coming Tuesday.
Me too. Thank you.
Okay, thank you.